Section 3.5, page 2. Now we've already mentioned that we're looking at inverse trigonometric functions, and we had used that kind of -1 exponent notation. But when it comes to trig, we can also, before the trig, list arc. So if we want the inverse of the sine of x, we're asking for the arc sine of x. So an arc prefix and a -1 exponent are the same thing. Now, I've used the word exponent because that's how it's often referred to, but keep in mind, it's not actually an exponent, right? It does not mean that we have the sine of x to the -1 where we're going to bring it to the denominator, right? But I hear it get called exponent enough, I'm doing it myself. So example 1, we're just asked to evaluate to find the solution to some inverse functions. So our first problem is the inverse sine of 1/2. So if it's the inverse sine, then it's the actual sine of something, that's the answer to our above question, is going to equal 1/2, right? Inverse functions kind of flip-flop their inputs and outputs. So I want to know the sine of what is going to equal 1/2. Let's go look, the answer's there obviously, but let's go look at our unit circle. We said the sine is the y value. Where is sine 1/2? Here it's 1/2, here it's 1/2, it's -1/2 in the third and fourth quadrant, so we don't want those. So we have found that in the first quadrant and the second quadrant, the sine is 1/2. Which one am I going to answer with? Well, we had mentioned earlier that our answers for inverse sine functions all need to be between -pi/2 and pi/2. Our answers can only be in the first and fourth quadrant. So if it's between the first and the second, then the first quadrant is going to be our answer, pi/6. Again, I'm asked to find the arc sine, exact same question as the inverse sine, but this time I have -√3/2. So the sine from what that's in our domain, because now we need to look for that, has a y value of -√3/2. As I come up here, +√3/2, +√3/2. Now here's -√3/2 and here's -√3/2, but we said it's only from these domains, the first and the fourth. So it feels like I want 5pi/3 to be my answer, which is what I wrote right here. But we talked about how our domain goes from -pi/2, our range, pi/2. So when we're in the fourth quadrant, even though 5pi/3 is in the fourth quadrant, we want to think of it as swinging clockwise from the x-axis to be -pi/3. Arc cosine of √3/2. So the cosine of what equals √3/2. I mean, you can see the answer here is pi/6. Remember, the cosine is the x value. So here is our x value, negative over here, negative over here. And although it's positive over here, we also said our sine answers only come from the first and second quadrant. So our √3/2 comes from pi/6. Obviously, you've noticed the pattern we're answering in terms of radians because we were not asked for degrees. Cosine inverse of the -√3. Well, in this case, when we're staying in the first and second quadrants, we've got 5pi/6. Now, the tangent is going to get a little bit funkier when we go to solve this one. The inverse tangent of 1. So when does the tangent equal 1? Looking at our unit circle doesn't necessarily help. So I need to think of tangent as being sine over cosine, sine divided by cosine. Now in this case, because it equals 1, Really, we want to know when are the same values, when are the outputs the same, when are they equal, so they cancel to 1. I kind of mentioned, I've seen a student before, I thought this was clever, kind of cross multiply. And they said, that's just going to give me sine of 1, that's just going to give me cosine. I said of 1, but I meant cosine. So when are the two values equal? They're obviously equal at some rotation of pi over 4. And since we're going from the first and fourth quadrants, then they're both positive up in the first quadrant. Okay, arctangent of the square root of 3. I'm going to go back to that sine over cosine model, but I don't know that cross multiplying really helps because square root of 3 cosine doesn't look familiar on the unit circle. So here's what I know. All of our functions, all of our values are fractions over 2. So I'm going to think of each of these as being over 2. So when does the sine equal positive square root of 3 over 2? When does the cosine equal positive 1/2? Or were they both negative, but in my domain? And the only time it's in my domain is pi over 3. Okay, now 2 pieces, one to help you understand where the derivative come from, but also to help you get the derivative. What if I was asked to simplify the tangent of an inverse trigonometric function? So this is really confusing to look at. Let's just think of this as the tangent of theta. That's so much easier. Now, for that to be true for our question, theta is going to have to equal the function we want, but somehow there's a simplicity to this statement that's a little bit easier to find. Generally, we had been asking ourselves with inverse functions, the sine of theta equals 1 over x, what's theta? But in this case, it doesn't really help because we only need numbers from the unit circle and we don't have it. So we're going to go back to this statement that we wrote, and we're going to go ahead and take the sine of the left function, we're going to take the sine of the right function, and remembering that a function and its inverse kind of undo each other to just give you your input, then we can say the sine of theta is just 1 over x. This is helpful because we know the sine, SOHCAHTOA, the sine is the opposite over the hypotenuse. We can now draw our right triangle. We can put theta in the non-right triangle corner, and we can figure out what our opposite is. We know it's 1. We can figure out what the hypotenuse is. We know it's x. And so we just have an adjacent side that we can solve for using a squared plus b squared equals c squared, Pythagorean theorem. I can get the adjacent squared is x squared minus, 1 squared is 1, and so I'm going to take the square root of both sides. The reason I want that is go back to what do we really want to find. We want to find the tangent of theta, and we know that tangent, SOHCAHTOA, is opposite over adjacent. In our triangle, the opposite is 1. The adjacent we just solved for to be this radical, and so therefore the tangent of theta is 1 over the square root of x squared minus 1. But remember, we were using tangent of theta where theta is actually the question asked. So the question asked has the same answer. Okay, here's where that is helpful. What if I was asked to take the derivative of an inverse sine? Now, this is going to turn out to be the formula, but let me go ahead and show you where it comes from. We're going to prove it. So again, I want to take the derivative of an inverse sine. I don't know what the inverse sine's derivative is, so let's write it symbolically as, in this case, theta. So if we can find the derivative of theta, then we've also found the derivative of the inverse sine, which is what we're trying to prove. So I'm going to go back to the statement where theta equals the sine of x, and I'm going to take the derivative of the left side, and I'm going to take the derivative of the right side. I wrote take the sine of both sides. Oh, sorry, that's what we wanted. I said that wrong, right? We're going to go take the sine of theta, and we're going to take the sine of the inverse sine of x. We already said taking a sine of an inverse or a function of its inverse is going to just give you the input. So here is an equation that I can take the derivative of for the x variable, but on the left side, I'm going to have to use implicit differentiation because having the other variable theta. So the derivative of the sine is the cosine. The input stays the same, but now when I take the derivative of theta, which is not the variable of my function, I need to either write d theta dx, or I went ahead and wrote theta prime. The derivative of x is just 1, and I don't need to write dx over dx because that's also 1. So I've got this. I'm going to divide both sides by the cosine of x, sorry, theta, cancels it on the left, and makes it in the denominator. So the derivative of theta, which is the thing I want, which is equal to my answer, is 1 over the cosine of theta. But we got to go back to what we just did a moment ago. We need to find theta. So we had said that the sine of theta is x, right? I've just copied that over here. And we can think of that x as x over 1. And we know that the sine, SOHCAHTOA, is opposite over hypotenuse. So back to my right triangle, back to putting theta in an angle. The opposite side is x. The hypotenuse is 1. I can solve for the adjacent because of my a squared plus b squared equals c squared, subtracting the x squared to the right, taking the square root of both sides, so that now when I need to know the cosine of theta, and by definition, SOHCAHTOA, the cosine is the adjacent over the hypotenuse, I have a triangle where the adjacent I just found to be square root of 1 minus x squared. The hypotenuse is 1, so anything over 1 is itself. And the derivative, we said, is to put that cosine in the denominator. So we're going to put square root of 1 minus x squared in the denominator. We have just proven the derivative of the inverse sine of x.